Hello, my name is Xuanli Xu from Temple University, and I am presenting the paper Taking Graph-Based Classification Without Changing Existing Connections. I worked on this research with the Professor Xiaojiang Du from Temple University and the Professor Chang Zhen from University of South Carolina. Before go to our work, let's first look at the background. As we all know, graph data is ubiquitous for many real-world applications, such as social networks, communication networks, and so on. And this data can be presented as graph structure, which contains nodes and edges. For social networks, a node could be a user and the edge could be the connection between users. However, in such networks, in addition to normal nodes, there are usually some malicious nodes, as illustrated in this toy social network. So in order to detect this malicious node, many node classification methods have been proposed. Basically, node classification method can be roughly divided into two categories, which are graph neural networks and collective classification method. The first one, graph neural networks, are deep learning-based method. They can extract a special feature of node and learn the representation of graph nodes as feature vector to operate the node classification. The collective classification, it makes joint classification of connected nodes to address node classification tasks. It first defines the prior representation score for each node and then assign weights for edges. After that, representation scores can propagate along the edge to finally get the posterior representation scores and operate node classification based on it. However, the recent researchers found that such machine learning models are vulnerable to the adversarial attacks. This slide shows adversarial attacks by modifying graph connections. In the original graph, two malicious nodes can be detected by node classification system as positive. The attacker first chooses a subset of malicious nodes as the target node, which is the one inside the red circle in this example, and then modify the connections of the target node. The figure on the right-hand side is the graph after the adversarial attack. The red dashed line means the attacker removes the edge, and the red solid line means the attacker insert new edges between nodes. After such modification, the node classification system will mistakenly classify the positive target node as negative, evading the node classification system. Different from the attack mentioned before, our proposed attack is to add fake nodes to the original graph, linking them to the existing node without modifying original connections. In our proposed attack, we also choose this subset of the malicious node as target node. And our goal is to make the node classification system misclassifies both target nodes and fake nodes. In other words, both target nodes and fake nodes can be classified as negative. And in this paper, our attack targets at a linear loopy belief propagation classification system to launch a proposed fake node attack. The linear LBP is a collective classification method proposed by a group of the Nergon. It is defined by a chosen training dataset and the edge weight. The training dataset of the linear LBP is a small subset of labeled positive nodes and negative nodes, serving as a prior knowledge of linear LBP system to start the belief propagation process. And the rest of nodes are the testing dataset. In the linear LBP, the weight of each edge is the same. So the attacker's knowledge can be classified by these two factors. The attacker has full knowledge means the attacker knows full training dataset and the exact weight used in the linear LBP system. But sometimes the attacker may only be able to know the partial knowledge of the training dataset. or have no idea what value used for the weight in linear LBP system. And in order to find an effective way to link the fake nodes to the existing node, we formulate our attack as an optimization problem. The objective function is the total cost of creating and linking fake node to the original graph. And our goal is to find a matrix B, where each entry indicates whether insert an edge between node U and node V. The first two constraints means we hope to achieve false negative rate on the fake nodes and target nodes as high as possible. And in the last constraint, K, means the maximum number of the edges each node can have. We set this constraint to avoid each fake node connecting too many existing nodes, which may be a very suspicious behavior and can be easily detected. We launched our fake node attack on two datasets. One is Aaron dataset and the other is Facebook dataset. The average degree of Aaron dataset is 11. A node in Aaron dataset is an email address, and an edge between two nodes means these two email addresses send at least one email to each other. And a positive node stands for a spammy email address in the Aaron dataset, and a negative node stands for a normal email address. The average degree of the Facebook dataset is 44, which is much denser than the Aaron dataset. So each node in Facebook dataset represents a user, and two users are connected by an edge if they are friends on Facebook. A positive node means this is a malicious user, and of course a negative node means this is a normal user. And in these slides, let's take a look at the impact of value K and N for the Aaron dataset, where K is the max number of edges each fake node can have, and N is the number of new fake nodes added to the original graph by our proposed attack. And the upper part is the false negative rate on target node, and the lower part is the false negative rate on the new node. As you can see, our proposed attack can achieve the 100% of the 100% false negative rate on both target nodes and new nodes under many different combinations of K and N. And this slide shows impact of K and N on the Facebook dataset. Although almost all false negative rate on fake node are 100%, the false negative rate on the target node are only about 15%. This is because the Facebook dataset is much denser than Aaron dataset. And note that the attacker does not modify the existing connections in the original graph, which means it's much more difficult for the attacker to affect the target node under the strong influence from the original neighbors of the target node. And the previous results are obtained when the attacker has full knowledge of linear LBP system. And next, I'm going to show the result obtained when the attacker has the least knowledge, which means the attacker does not know the exact way or have the complete training dataset. So attacker can only use the substitute weight and the partial training dataset to launch attack. On the left figure, when exploring the impact of partial training dataset, we fix the substitute weight as 0.03. The attacker is still able to launch powerful attack with only 40% of the training dataset. And on the right figure, we assume the attacker has 40% of the training dataset, and to explore the impact of different substitute weight. As we can see, the result shows the false negative rate decreases as the substitute weight goes further away from the true weight, which is the 0.01 here. But the attacker still has a lot of chance to find a close substitute weight to make the attack successful. And this slide shows the result for the Facebook dataset. The trend is similar to the result of the parent dataset. And the low false negative rate of the target node is because the high density of the Facebook dataset, as explained before. And as we can see, the false negative rate of the new fake node could be up to 1. And our attack also can make the linear RBP system misclassify about 40% of the target node. So this is still can be seen as an effective attack on the Facebook dataset. And here is the conclusion of our paper. We proposed a new attack on collective classification methods by adding fake nodes without changing existing connections. And in order to find the neighbors for those new fake nodes, we formulate our attack as an optimization problem. And finally, our experiments show that our attack can achieve high false negative rate on both new fake nodes and target nodes, even if with only partial knowledge of the node classification system. And I'm happy to answer any questions. Thank you very much.